Hi, hello there, and welcome back to STEMI with Steve. Today we're going to go through how to multiply decimals together. Now, the concept here is really important, understanding which way the decimal point is going to shift, either to the right or to the left. If you multiply by groups of 10, you're either going to be multiplying by 10, 100, 1,000, and so on. And when you do that, the number is greater than 1, so it's going to make the number bigger, which will shift the decimal place across to the right. Whereas if you times it by 0.01, it's going the opposite one, and it's going to shift to the left and make the number smaller. So let's jump on in so you can see what I mean by all that. To start, let's have a look at these books questions. So if a single piece of paper is measured as 0.0102 centimeters long, how wide is the 1,000-page book? Now, hopefully you've understood the concept here, and you just times it 1,000 by 0.0102. Now, you could type that in your calculator, or you can count how many zeros there are, because this is in powers of 10. So 0.00, there's 3 zeros, and then we have 0.0102. So decimal points there. The number's going to get bigger, so therefore it's got to shift to the right, and just needs to shift across 3 times, which will give you 10.2 centimeters. Now, this example hopefully gives you something real world and practical. So sheet of paper is really, really thin. A book's about that big. That seems reasonable. And that's what you should do in checking at the end with your answers as well. So the lesson intentions today, we want to learn how to multiply decimals. We want to understand how the decimal shift works, and then apply these skills to some little practical problems at the end. So if we want to multiply by larger powers of 10, so 10, 100, 1,000, million, all that, we simply count the number of zeros in the number, and then we shift to the right by that number. So for example, 1.234 to 0.293 times 100, the decimal point's in the middle here, and we just shift it across 2 times. We get 123,429.3. Now this makes sense because the number is going to get bigger because we're times it by 100, and therefore the shift is as simple as that. So just pause the video and have a go at these ones. Awesome. So for the first one, 47.3, if we shift that across, it goes to 473. The next one, 0.2 times 1,000, we're going to shift the decimal place across 3 times, and we get 200. Same with this one. We're going to shift it across twice, so we get 45,323.2. Times them by 10, we just shift it across once to the right, so we get 0.02832. And the last one, we're just going to shift it across 4 times. So then we get the number, let's have a look, 46,723,231. Cool. So when you multiply by smaller powers of 10, so decimal numbers, it's really easy. We go the exact opposite way. We shift to the left because the number is going to get smaller. So if we have this number here, 123.293 times 0.01, same again, decimal points there. We count how many loops to go back to 1. So there's 1, 2. So we're going to go this way, 1, 2, and shift it across. So that goes this way, and then we get 12.34293. Now, if we think about this logically, it's the same as times it by 1%. So if you had over nearly $1,000 in the bank, if you found 1% of it, you get about $12. It's another way of thinking about the link there. So just pause the video, have a go at these guys. Great. So for the first one, you should see there's 2 loops, 1, 2. So it's going to go back 2 loops, and you get 0.345. This one, 0.7 times this. So we just focus on the 0.1 part, 0.1. So 1, 2, 3. This is going to go back 1, 2, 3, and give you 0.007. The next one, it's only going to shift back once. So you get 85.3232. And the last one, second last one, we're going to shift back 1. So just jam another 0 in there. So 0.0002832. And then this one, 1, 2, 3, 4, 1, 2, 3, 4. So that we get 0.675232231. Now, if we multiply numbers where it's not a power of 10, we've got to apply that same principle, but we also times the numbers together. So for me, what I do in my mind is I try and shift this back to be a whole number. So this is 25 times 4. And then I count how many loops I've done. So I've done 1, 2 here, and then 1 there. So therefore, once I find my answer, I just have to do 3 loops back. So the first question in my mind, I do 25 times 4, which gives me 100. And then I just shift it back 3. So from that, we basically shift it back 3, 1, 2, 3, and we get 0.1, which kind of makes sense. If we had a quarter of 0.4, or we had 40 cents, and you had to find 25% of it, it would equal 10 cents. And you can sort of justify it that way. Have a go and see if you can use that technique with this one. Cool. So the first step is you do 15 times 7. You can either write it out manually or type that in the calculator and you get 105. Then we count how many loops. So 1, 2, 3. So we're going to go shift it back 3 loops, which then gives us 0.105. Awesome. To give a bit more structure, if it gets a little bit more complex, so this number here, you can write it out like this and then count the shifts back as well. So you literally go through and do times tables as normal, just forgetting where the decimal point is to start and forgetting about zeros. So 2 times 6 gives you 12. 5 times 2 gives you 10, and then plus 1, which then gives you 11. And then 2 times 2 gives you 4, plus the 1 gives you 5. Then you need to count back how many decimal points you've got. So in this case, we've gone back 2. This one's gone 1. So then we need to shift this back 3. And then we get 0.5012. Now, obviously, you can also use your calculator as well here, but understanding and practicing with these long multiplication methods does help you understand a bit better exactly how to do this. So just pause the video, use your technique, and have a go at that. Cool. So for the first one, you should have got 165.2. The next one, you should have got 7.062. The next one, 321.86. And the last one, 3.04. Now, all these numbers seem pretty reasonable. So what I usually do is I just look at the integer parts, and see roughly if they make sense. So 2 times 3 is 6. Is 6 close to 7? Yeah. It's got a little bit more on the tail, so that's why it's close-ish to that. So you should never get these wrong if you just quickly have a little look at the front. So for example, 7.6 times 0.4, or 40% of it, it's close to 50%. Yeah, that seems reasonable. The other way that you can do it is with long multiplication. So if you've got 2-digit numbers, you can go through this process as well, exactly the same as what you've done since grade 4. So 7 8s are 56, so you put a 6, carry the 5. 3 8s are 24, plus the 5 gives you 29. And then 1 lot of 7 and 1 lot of 3, but we need to jam a 0 here because it's the tens column. And then we get 37. We then go through and add that together. So we got 6, 6, and then carry the 1, and then we also get a 6. So we've got the devil's number. We then go through and count off how many decimal place shifts we've done. So 1, 2, 3, 1, 2. So we're going to do 5 loops. So 1, 2, 3, 4, 5. And then we put in the decimal point. So 0.00666 is what this number would work out to be. Now, again, you could just type that in your calculator, but by practicing this skill, getting your times tables and all that, it is quite valuable. So just pause the video and use your technique. Cool. So for the first one, you should have got 177.8. The next one, you should have got 802.7. Next one, 7,164. And the last one, 62.93. So a little bit more of a problem-solving question. Just pause the video and have a go at that one. Cool. So a laboratory is conducting experiments on chemical reactions that release energy. In one experiment, they mix 2 solutions, solution A, which contains 25 mils of a chemical compound, and solution B, which contains 75 mils. When mixed, the reaction between these solutions released energy at a rate of 134.2 joules per litre of a resulting mixture. Calculate the total amount of energy released by the reaction when the entire quantities of solution A and solution B are mixed together. Express your answer in joules. So first step, you've mixed the total mixture together, so 25 plus 75, which gives you 100 milliliters. You then work that out in liters, so I would convert that back. So we get 0.1 liters, and then we times the expenditure by that amount. Now, the reason we changed it into liters is this measurement was joules per liter. So we need to make sure we're able to convert into the same unit before we times them together. Then we times it, and we got 13.42 joules. A little bit more complex. Pause the video, have a read, and see how you can go. So, aerospace company is engaged in the production of composite panels using the construction of spacecraft. Each panel incorporates a central microchip sensor that monitors structural integrity during flights. The microchip sensor weighs 0.0375 kilograms and is encased in a special polymer frame that weighs 0.0921 kilograms. Due to safety regulations, each spacecraft requires panels to be arranged in a specific pattern where the number of panels varies for each section of the spacecraft. Order requirements for the upcoming space mission: the company must produce sections of the spacecraft with the following requirements. The control section requires panels arranged in 17.25 rows with 14.6 panels per row. The habitation section needs the panels in 29.4 rows with 9.3 panels per row. And the engine section needs a denser arrangement with 34.7 rows and 18.1 panels per row. We calculate the total number of panels required for each section of the spacecraft, determine the total weight of the microchip sensors for their polymer frames for each section, and then sum the weights from all the sections to find the total weight of the microsensors and frames needed for the mission. Given the complete spacecraft section must be tested for weight and balance distribution, then calculate the average of these sections. Cool. So the first part here is going to work out the total panels for each section. So just simply times those two numbers together to work out the area. So there's 251.8785 panels, 273.42 panels for the habitation section, and then the engine section, because it's a little bit denser, has 627.97 panels. From that, we then work out the weights. So the weight of one microchip sensor is 0.375. Weight of a polymer frame is 0.921. We add those together and we get 0.1296. We then work out the total weight for each section. So we times the number of panels by each of those weights. And we leave that in two decimal place. So you got 32.961, 35.41, and then 81.39. The total weight then for the mission is adding all those together. You get 129.47. And then lastly, the average weight per section is the total, the 149.47 divided by 3. So we get 49.82 in each of those sections. Cool. There is a Dr. Frost attached to this. Have a crack at the decimal multiplication homework. And yeah, hopefully you've picked up on a few patterns there. So that's it from me with decimal multiplication. Hopefully you've picked up basically just times in by a larger number than 1. You're going to be shifting the number to the right. Whereas if you times it by a number that's less than 1, it's going to be shifted to the left. If you remember those two rules, it should be pretty easy. Thanks again. Hope you've enjoyed and learned something along the way. If you did, please give us a like and subscribe down below, as it does help with that YouTube algorithm. And yeah, thanks again. See you next time on Steaming with Steve. Adios.